Greetings and congratulations. You have worked hard to get to this point, spending many hours in the library and the laboratory, in the classroom and the carrel. After all your effort and the support from family and friends, I can only hope that your teachers have taught you something, and that you now know more than you did when you arrived. But this puts me in mind of my oldest friend, who after graduating from Chicago as an undergraduate, went on to medical school. During his first year, he often exclaimed how much the medical profession knew. However, in his last year, his tune had changed, and he bewailed that medicine knew so little. I confess that I have felt the same way. When I started as a physics graduate student, I was in a panic to learn enough to pass the required exams. And now I look around and realize that we understand so little of what we see. This is what I wish to talk about today. The earliest questions in physics often related to daily experience. How did objects move? Why couldn't heat be transferred directly from a colder to a hotter body? Modern science has progressed far beyond that point. The great allure of physics has been to delve to the ever smaller or ever larger aspects of our world, eschewing the middle as mundane. We know the elementary particles that make up visible matter. Right here, work at Fermilab's Tevatron discovered the top quark and made predictions about where the Higgs would be found. The world rejoiced when the Higgs was finally discovered this past year at CERN. We know about the Big Bang and that the universe expands at an accelerating rate. At extremely low temperatures, we understand, due to work in our Provost lab, about the nature of the pressure-driven quantum phase transitions. These are deep and important discoveries. This is, we think, what modern physics is about. But there's physics to be learned in the more ordinary world around us. Let me give you an example. I hold in my hand two forks. You can all see what they are. Now I ask you, which one of these would you want to plug into an electric outlet? Caution, the answer could kill you. The wrong answer could kill you. Okay. So, clearly, the way an object looks foretells about how it carries electricity. Now, if you want to stir boiling water, which of the two forks would you use so as not to burn your fingers? Again, you could tell just by looking. The optical properties of material, that is, the way it looks, are related to its electrical and thermal properties. Why is this? It is an old question, but one that gets to the heart of how the world around us is made up. I like this question because it also shows that simply by observing the world, yes, just with one's eyes, one can identify important scientific questions. I have just finished an experiment of co-teaching a course with a sculptor-architect. In this course, sponsored by the university's new Gray Center, our goal was to explore the role of observation in our different endeavors as artists and scientists. We asked our students to observe aspects of the light around them and create an artistic project that made use of the science of their observation. Our hope was that we could find a realm where an investigation could give satisfaction both on scientific as well as on aesthetic or emotional grounds. Having been in a physics department all my adult life, it has been tacitly assumed, if not required, that the only relevance my work could have would be strictly scientific. Any hint of emotion would detract from its impact and reliability. I keep wondering if there is another department in a university where both sides of human experience could be equally expressed. It is perhaps the department of the indefinable, and as far as I can tell, it sadly does not yet exist. The issue of how to observe is important for art and science alike. It has been addressed in novels and drama, as well as in philosophic texts. Victor Hugo, in Les Miserables, asked, "Where the telescope ends, the microscope begins, and which has the wider vision? You may choose." Hugo foretold one of the grand syntheses of physics, that astrophysics and cosmology, concerned with the structure of our universe, is deeply connected to elementary particle physics, concerned with the very, very small. But Hugo then continued, "How do we know that the creation of worlds are not determined by falling grains of sand?" He understood, even before the advent of modern science, that the workings of our world are wrapped up in things we can touch and see with unaided vision. This thought was explored explicitly by Tom Stoppard in his play Arcadia, which contemplates chaos in our lives. There he has a modern-day protagonist exclaim, "It makes me so happy to be at the beginning again, knowing almost nothing. People were talking about the end of physics. Relativity and quantum looked as if they were going to clean out the whole problem between them. A theory of everything. But they only explained the very big and the very small. The universe, the elementary particles. The ordinary-sized stuff, which is our lives, the things people write poetry about, clouds, daffodils, waterfalls, and what happens in a cup of coffee when the cream goes in, these things are full of mystery. We're better at predicting events at the edge of the galaxy or inside the nucleus of an atom than whether it'll rain. We can't even predict the next drip from a dripping tap when it gets irregular." Then he goes on, "The future is disorder. It's the best possible time to be alive when almost everything you thought you knew is wrong." So much for what you learned in your classes. The playwright's proposal is that we know almost nothing and that almost everything we have taught you is wrong. Is this really the case? What science also teaches is that our knowledge can be tested by rigorous experiment or logical analysis, and that we can learn from our mistakes. This is perhaps what is missing from Stoppard's account. Earlier in the play, another conversation occurred. When you stir rice pudding, the spoonful of jam spreads itself round, making red trails. But if you stir backward, the jam will not come together again. Indeed, the pudding does not notice and continues to turn pink, just as before. We must stir our way onward, mixing as we go, disorder out of disorder, into disorder, until pink is complete. I'm perturbed by this conclusion and would like to see if experiment can shed light on this passage. So, I have assembled before you a classic experiment. I have two plastic cylinders, and in between them, I have a liquid. And I am next going to inject a dye into that liquid. So if I can do this. This is the worst lab coat I've ever owned. Okay, and so I'm going to inject a dye. I have made a C, standing for Chicago, our home. Okay, now I'm going to turn the inner cylinder, so everyone should see. You can see over there. Okay, good. Good. Okay, so now I'm going to turn this, and it gets mixed up. Okay, so Tom Stoppard seems to be correct. The dye is mixed with the other fluid and has disappeared completely from view. But now I'm going to employ my powers as a physicist and try to reverse time. Okay, I turn in the backward direction, and let's see what happens. Behold, the letter C has now reappeared. We've recovered our home. I assure you I have not played a trick. I have simply demonstrated a theorem in fluid mechanics. But I hope you agree it is certainly surprising and counter to intuition. What is the point of this demonstration besides trying to surprise and entertain you? It is that nature has this disturbing tendency to do what it wants rather than what you expect. If we accustom ourselves to careful observation, we can find other examples in abundance. But first you have to think about what you expect and be willing to realize that you were surprised. To explore these surprises in pursuit of underlying principles is one of the sacred and magisterial jobs of science. I do not deny the importance of searching for first causes and for finding a theory of everything. And there is, indeed, beauty and inspiration in large-scale science and technology. The great instruments of science leave us full of awe. Rupert Brooke, in his poem, The Great Lover, called it the keen, unpassioned beauty of a great machine. But there are also more delicate sources of beauty in the more mundane examples of science that invest our daily experience. I would like to argue that they're even more important to us since they are responsible for the texture of our lives. This is not the only reason that they should be explored. Nature tends to use the same set of principles over and over again at different scales. The same mathematics and physics used to predict the Higgs had first been used to explain superconductors. Nature, as well as history, repeats itself. As the philosopher Alfred North Whitehead said, we notice that a great idea in the background of dim consciousness is like a phantom ocean beating upon the shores of human life in successive waves of specialization. I hope that the course in Science and Art that I just finished co-teaching will have an influence on our students. I hope the scientists in the class will continue to reflect on the aesthetic aspects of what they will be doing in their future work. I hope that the artists will see observation as a skill and science as a way to gain intimacy with their subject matter. Science is powerful in its predictions, but is also powerful as a metaphor. The experiment that I did for you today showed a surprising property of fluids, but I hope you also take it as a metaphor. The C stood not only for Chicago, but also for how you learned to think during your time here. That is, what you really learned in your classes. In your life, you will go out, and you may believe that much of this education has been lost in the turbulence and disorder of your lives. But I hope this demonstration shows that no matter how faint the trace may be, you can always turn times backwards and come home. May you return often. Thank you.